So I'm going to try and finish chapter 3 today, if possible, so we can start a fresh chapter on Friday. If I have to, I'll leave a couple of slides over, but I'd rather not. So we'll see how we get on. That doesn't mean, though, that I don't want you to turn your microphones on and ask a question if I'm not explaining something in a way that you are understanding, okay? Because that's important. You need to be able to follow these ideas because they impact what we see when we're looking at those developmental trends on the skills, all right? So remember that Newton's first law is to do with objects at rest or objects in motion, that they're going to stay in that form, in that situation, unless a force is applied to them, okay? So what that means when we are looking at teaching skills is that we have to be able to exert this force, right? And to exert it, we have to be able to produce it. And so we're looking at the muscular system here, how strong are a particular set of muscles, do we have balance on either side of the body, okay? So we've got to be able to exert this force to move objects. That object could be a javelin, or that object could be myself, right? And it means we also have to be able to apply a force to change direction or change the movement, right? So if I want to cut around someone, I have to be able to apply a force that changes me from moving forwards to moving sideways. Okay? Inertia's connected to mass. Hopefully you took a little look at these terms after class on, what day is it today? After class on Thursday. More inertia, so the bigger, the heavier the mass of the object or the person, the harder it is to move that object, and the more force application is required. So this is a lot for the brain to learn when you're working with a beginner, whether that beginner is a small person or a teenager or an adult, right? The brain still has to learn how and when to apply force effectively, all right? So, for example, when we're learning to swing a tennis racket, right? The initial learning curve the brain has to go through is how do I apply force to get that tennis racket moving? But then, once it's moving, now the brain has to work out, well, how do I apply a force to stop it moving? Otherwise, what we get is going round and round and round in a circle, right? So that's a lot of coordination of muscle groups, of muscle fibers within a particular muscle, right? Which fibers do I fire and contract to do which job, all right? So it's a lot of learning going on in the brain at this point. So in sport and in some recreational activities, often the goal is to be able to move the object further and or faster, right? So to do that, I have to increase the amount of force that's delivered to the object. Well, that's obvious, but how do I increase force in a particular situation, right? It also means that I can increase the distance over which the force is applied. So So if I can increase the distance that I'm applying the force, I get to apply the force for longer, right? So think about what constraints might affect these parameters, okay? Individual constraints. So when I'm talking about the person, okay? So we've already mentioned that to increase force, I have to increase the contraction in the muscle, which means the muscle has to be stronger, right? What about increasing the distance over which the force is applied? So really good visual example here is a highly competent baseball pitcher, right? Think about that in your head. What does that look like when you see someone who's a really top-class baseball pitcher and they're increasing that distance, right? What might be some constraints that could affect the distance that they can step? Jean, what do you think? Hello?
What was the question, Dr. Wall?
What constraint might impact that baseball pitcher's ability to take that huge long step that they take? So within the body, an individual constraint that might impact that huge step. Some of them look like they're doing the splits, right?
If he had a previous injury before that he's still recovering from, could that be considered a constraint?
It could be, yeah. What kind of injury might impact that step?
Maybe a hamstring tear, ACL tear in the knee.
Okay.
Yeah, hip injury.
Okay, good. All right. So those would definitely impact. What about his flexibility? How flexible does he have to be to take that huge step?
Extremely.
Right. Okay. So it doesn't always have to be something dramatic, right? The injury answer isn't incorrect. That would definitely change that distance. But it doesn't, think a little bit more subtly, right? If I'm going to take that huge step, I've got to be able to do almost the splits, if not the splits, right? Okay, does that make sense?
Yes.
Yeah.
Yes, ma'am.
So, adding distance then, we have in some skills a couple of different choices that we can combine to add distance. I can add linear distance to apply the force over by increasing the step length. Okay? I can also increase rotational distance by increasing the range of motion that I'm swinging the leg or the arm through. Okay, so I'm going to try and switch to the video. If I'm increasing step length, then from a complexity point of view within the skill, we're making the skill less stable, right? Because to increase the step length, let me take my shoes off before I break my ankle. Right, to increase the step length, I have to be able to stand on one leg for a longer period of time, right? So 1 foot is much less stable than 2 feet, okay? If I'm going to increase rotational difference, then my range of motion in the joint becomes very important, okay? So, let's see if we can get this to work today. We'll come out of that. We'll go to share screen. Oops, I don't know which clip it's going to be. Let's have a look. I've got two. No, not that one. I want the other one. Okay, see if I can make this bigger. Here we go. So, let's see if I can slow it. They haven't given me a slow version of this one. Please. See if we can go a little bit frame by frame. So watch his right leg. So that knee is behind his hip, so he's got his hip flexors are really supple, right? He took a huge step in because he still hasn't hit the floor, and he's got this massive range of motion in the rotational direction. So you can see force application is really nice there, right? Sorry, I have to keep switching backwards and forwards because I can't get it to... So when we're coaching this, or teaching this, then what we're looking for is the optimal relationship between instability and range of motion. Right? We don't want to make the skill so unstable that the individual falls over. Right? And we don't want so much range of motion that they're not able to control that limb. So we're looking at this optimal relationship between force and distance, right? And we need to try to remember to coach both of those, not concentrate just on one or the other. All right, so law number 2, remember I said there were 3 laws. So law number 2 says that an object's force is related to its mass and its acceleration, or F equals ma. Okay. Now we can flip that formula around, and then we know that acceleration of the object is related to its force divided by its mass. Okay, force over mass. If we're at constant velocity, so another way to think of A is the change in velocity over the change in time. So I have 2 ways to calculate acceleration. Right? The second way is useful to understand the relationship between the velocity and the acceleration. What if I'm looking at, let me write this on the whiteboard so you can actually see it. Hold on. Oh, I hope you guys come back to school soon. Whiteboard. Okay, so A equals a change, that's a triangle, in velocity divided by a change, oh that one's better, a change in time, right? So if velocity is constant and not changing, what value is A? If there's no change in velocity, then this would be 0, right? So what would be the value of A?
Would it be undefined?
I think you're complicating it a little bit, Kayla. It's simpler than that. If I divide 0 by anything, what do I get?
0.
Well done. Good. Okay. So, if velocity is constant in any direction, I don't have any acceleration occurring. Right? The only way to get acceleration is to change velocity or deceleration, all right, negative acceleration. I have to change velocity. That involves force production. Okay. So it's interesting to think about the second law with sport, because we can think about what happens if my object is a, it's going to make me do this every time. Jeez Louise. Right? What if my object is a shot put compared to a basketball, right? The mass of a shot put is much higher. So if I'm going to accelerate that shot put, throw it from 0 to some speed, I have to apply a huge amount of force. If I'm going to accelerate a basketball, I don't need so much force application. Does that make sense? So that's a really great teaching tool, okay? Because on any given day, I can't change the force application, right? I can't make someone stronger on that day. So on any given day, a person can only throw as hard as they can on that day, right? So I can't, as the teacher, when I'm looking at this equation, I can't manipulate F to improve the throw or improve motivation and success, right? So I've got either the mass or the acceleration to play with, right? So that means then, let's say we're in the gym and we're doing a throwing lesson, right? And the goal for the PE student is to throw the ball and hit, I don't know, something, maybe a big sheet of bubble wrap on the wall, right? Because that's always fun when it goes pop, okay? So, and I'm watching the students, I'm correcting them, I'm trying to get them to take a bigger step in opposition, to maybe swing their arm harder. And I've got a couple of children who just cannot get the ball to the bubble wrap, right? So they're not getting the fun of the activity. And again, if I'm not having fun, if I'm not being successful, then that's demotivating, right? And so I'm watching the class, I'm moving around, and I notice that a couple of people are just not making the goal, right? And they're getting irritated, and I can see them thinking about, I'm just not going to bother trying this anymore, this is a waste of my time, right? What can I do to help them be more successful, right? I think instinctively you would do this, but one of the things that will make you a really great teacher or coach is to not always do things by instinct, to understand the physical laws that are in place here. What would you manipulate? What would you change out for that student that can't get the ball all the way to the wall?
Probably use another target, maybe, instead of getting.
Move them closer to the wall.
You could move them closer to the wall, but then that makes them look very different to everybody else in the room, right? Which might be a bit embarrassing. What piece of equipment could you change?
Can you change what ball they use?
Absolutely, you're the teacher, you can do whatever you like, right? So instead of moving them closer, because that makes them very, very different to everybody else, you could give them a lighter ball that they have enough force to apply and get to the bubble wrap, right? So by changing the mass of the ball, I increase acceleration. And if I increase acceleration, the ball is going to fly further. Right? So it's important as the coach, as the teacher, that you have multiple options of equipment available to you, so that you can teach everybody in the group, not just the kids who are already competent. Okay? So, law number 3. Closely related to what we were talking about with law number 1, right? And law number 3 is usually the one that people kind of know because they've heard it. For every action, there's an equal and opposite reaction. Right? So that means that when I push on something, when I push on an object or a surface, that object or that surface pushes back. So on Thursday, we were talking about walking, right? And I was saying that I can walk forwards because I'm pushing on the floor down and backwards. And therefore the surface pushes up and forwards. That's my external force, right? So these two, law number 1 and law number 3, have quite a lot in common, right? Law number 1 is saying there has to be an external force. Law number 3 explains where that external force often comes from. Right? So, and I think hopefully this picture of the footsteps in the sand give you a good picture of this, right? Because what happens when we walk on sand, because when I walk here in the classroom, I don't leave footprints, right? When you walk across the car park on a dry day, you don't leave footprints because the surface that I'm walking on is strong enough to push back at an equal level. Right? When we walk on sand, the surface tension of the sand isn't strong enough, right? So our foot sinks in a little bit before the sand pushes back. Right? When we push on something, it pushes back. Questions? So we use this concept, again, possibly not consciously, which is what class is all about, right? Because if you're an experienced athlete, there are things you would do to help someone correct a movement, but do you know why you're doing them, right? The why is important because the why is what makes you a better teacher, a better coach. Right? So this idea of law number 3, and you can find these videos at the website. I'm not going to play every piece of video in this PowerPoint, otherwise we'll be here until tomorrow, okay? This is the young lady we watched before who uses a backwards arm swing, which I'll talk about in a minute. And this piece of video of running, this young man has a very strong arm swing, but you can see from the kind of stopping point here that the arm swing is a little bit across his body rather than forward, right? So law number 3 is involved with this idea of oppositional arms and legs, oppositional movement, right? So next time you've got enough space around you, okay, try standing up and just swinging your free leg as hard as you can and see what happens, right? If you hold your arms still, eventually you fall over, right? If you allow your arms to do their own thing, eventually your arms will start swinging in opposition because for every force, there's an equal and opposite force, right? So it plays a role in this idea of oppositional movement and directional force. Now, interestingly, we said that this arm swing, you know, she's swinging backwards instead of swinging forwards for her long jump. But if what she was trying to do was jump high, this arm swing is actually quite effective. Right? Because I stop my arms and that force that I've applied there gets transferred into my body and lifts me up. Right? But it's a really inefficient arm swing for trying to jump forwards. It doesn't work at all. So, the idea here, exerting force in the primary movement plane. So what is the plane of motion? All right? And this comes back to the idea of arms and funny feet action. Okay? We want to apply force in the plane of motion that I want to move the object. Okay? We don't want to add in additional rotational movements outside that plane that reduce the force application in the direction I want to go. Right? So, if I'm swinging my arms like this when I'm running, I'm applying force here when what I'm trying to do is run forwards. Right? So I'm reducing my force application forwards by swinging my arms across my body. That slows me down. Right? So immediately one of the things I want to correct as the teacher is to try to get this arm swing here. If speed and force are important, so if you watch a 100-meter sprinter or a 200-meter or even a 400-meter sprinter, you will not see this arm action. Right? But if you watch a 10,000-meter runner or a marathon runner, you might see this. Right? Because it's more about endurance and speed over the whole race than speed and distance within a very short period of time. So even though this is not as effective, right, it doesn't impact the performance in the same way as it would for a sprinter. Right? The other one you can look for, which you can get if you stand behind someone, right, is to watch what their free leg does as it swings through, right? If it kind of swings in a bit of a circular motion, then they're adding force rotationally instead of just driving straight backwards. Right? So if you see that kind of weird swing through, then you know you've got to work on pushing straight back. Okay, let's take a couple of minutes. Breathing space, brain space, because that's a lot of information. Okay, so let's go, where are we here? 10:07, so let's be back at 12 minutes past 10. So if you need a toilet stop or anything, or go grab a glass of water or whatever, that's what I'm doing, going to get water. Gasping. Oh, my new College of Education mask. Now I'm official. so dry. Okay, is everyone back?
Yes, ma'am.
Yeah, okay. All right, so the next concept that I want to introduce is looking at projecting an object, right? And to project an object, it's often involving rotating a limb, okay? So, again, I'm going to use the whiteboard and see if I can draw. So back in school, okay, this is not a very good circle. Pretend that's a circle, all right? Back in school, either on the playground or in a physics class, right? They would have taught you about what happens if I hold a ball or I hold a rope, right? And I swing round and round and round and round and I release the object. What's the trajectory of that object? Do you remember? Does it continue going round and round in a circle once you've let go of it? No. So where does it go? Is that Graylin? Or was that Jean?
Yeah, that was me.
Yeah, but I can't see you.
Oh, I'm sorry. No, that was Gene.
Jean? Okay, so where does it go? It doesn't continue going round and round in the circle. What happens to it? Do you remember?
I know for a fact it doesn't keep going around the circle.
It doesn't, right? When you release it, it flies off on a tangent to the point of release, right? In a straight line. So this is linear velocity equal to rotational velocity times the radius of rotation, which I don't know how to, I'm going to do that. Okay, so linear velocity when you release the object is related to rotational velocity multiplied by the radius of rotation. So how big is the circle, right? Now it's going to make me go all the way back through these silly slides. Why won't it just let me scroll down the side of it? Oops. Okay, did it then. Aha. Here we go. Right? So if I want to increase the speed of a ball or the speed of the object that I am projecting, right? So that could be throwing, it could be kicking, okay? Then I can do one of two things or preferably both together, right? I can swing it faster, so that increases rotational velocity. And I can increase the length, the radius, at the point of release. Okay? So this is something we see change quite dramatically from beginners to people who are experienced and good at skill. All right? So when I'm learning to throw a ball, right, I don't swing my arm very fast. I might get stronger and more mobile, and that allows me to swing my arm faster. But often what you'll see with beginners is that at the point of release, the arm is bent. Right? This shortens the radius of rotation. Because here's my center of rotation, my shoulder. Right? So if my arm is bent when I release the ball, I'm not going to see as much velocity on the ball as I could do if I can correct that so that at the point of release, my arm is straight. Right? A really good example is a tennis serve. Okay? If you watch someone who's not very good at serving, right, then as I make contact with the ball, often my arm is bent. Right? But if you watch someone who serves really, really fast on the international tennis circuit, when they make contact with the ball, right, their arm is straight, they're lifting up, they've got their racket all the way up, and the ball's all the way up there. And the velocity on that ball can be 150, 160 miles an hour. Okay? What's interesting, particularly if you work with the age group that are going to be going through puberty, is that increase in relative length occurs with that growth spurt. Right? All of a sudden their legs and their arms get longer. And so just because they grew, the velocity of the ball will be faster. Right? So you have to be a little bit careful, because that ball going faster doesn't mean their technique got better. It means their arm got longer. Right? So it doesn't mean that you don't still have to work on technique there. So, if we know that having the biggest radius possible gives us the most velocity, why then don't we keep the arm or the leg straight throughout the whole swing, right? If you've ever watched a cricket bowler, I think it's a lot more obvious in a cricket bowler than in a pitcher, possibly. But if you watch a cricket bowler, as they run up, they've got their arm really bent. They take their arm back bent, and then as they go to release, they straighten their arm. Right? Well, according to the rule, I should keep my arm straight the whole way round, right? The problem with that is that the limb that you're swinging has more inertia when it's straight than when it's bent, right? So if I keep it straight the whole way round, that takes a heap more energy to initiate than if I bend it and straighten it right at the right time. So that's where the technique portion comes in, right? I can keep it bent through the swing, but I've got to time straightening the limb with the point of release. Right? Inertia, when we're looking at rotation, is the mass by the rotational radius. Okay, so I've got the little boy here. We watched that piece of video last week. So try to visualize what you saw him do. It's either, I think we watched this piece, or we watched the little girl that was similar. Right? And then look at the development of the skill when we switch to right? Play again. So we're bending it, 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 we're swinging it really hard, and at the point of contact, the leg straightens. And he has a little bit of work to do on that. His knee is still a little bit bent. You can Google soccer and you'll get some really super examples. If you watch, particularly like a penalty kick, if you can get a bit of film that you can stop, and you'll see, right? Them straighten their leg right at the minute that they hit the ball. Which is why the velocity of that penalty kick is so fast. Aha! Sussed it, finally. That took me long enough. Questions? Is this making sense? Can you see how it applies to understanding those developmental sequences that we were looking at?
Yes, no.
Yeah? So, force absorption is a similar concept, right? So this time, instead of applying force, we have to deal with the force, right? So the concept, the principle is very similar, all right? If I want to stop the object, instead of projecting the object, then the easiest way is to increase the time over which the force is applied. Right? So, in gymnastics, they make the landing pads quite soft, so that when the gymnast hits the floor, they've got time as their feet sink into the mat to absorb all that force, because you've got rotational force, you've got gravity pulling on their body, right? They hit the floor with a lot of force. So we put a nice soft mat there to give them time to absorb that force. Okay? If you were teaching or coaching catching, right? And your person is standing like this, and the ball hits their hands and bounces back out again, what would you tell them to do with their arms as the ball hits their hands? Instinctively, what would you tell them to do with their arms? Right? If I'm standing there like this, what are you going to tell me to do? Go on, give it a try.
I would say with your
Repeat
arms.
the question one more time.
Sorry?
Could you repeat the question one more time?
Sure. So if I'm working with someone who's standing to catch the ball like this, right? And I throw the ball and it hits their hands and bounces back out. Right? What am I going to tell them to do with their arms as the ball hits their hands?
Other than prepare to grab it, I can't think of anything. I thought you meant like the trajectory of the ball, like tell them wherever their arms go. I mean, wherever the ball goes, that's where their arms need to go. I thought that's what you meant.
Okay. Let me rephrase it then. So, let me put it the other way around. Would I teach someone to catch the ball with straight arms?
No.
What do I tell them to do?
I guess bend your arms.
Right. Isn't that what you do, right? If you watch people catch a ball, they catch and they pull it in. Does that ring a bell, right? Can you see that in your head? Great.
Yes, ma'am.
Yeah, right? We do this because of this, right? If I keep my arms straight, the reason the ball bounces back out is all that force of the ball hits my hand applies force back, and the ball bounces out of my hands. But if I absorb some of the force by bending my arms, makes it easier to hold on to the ball. Right? I increase the time over which the force is applied to my hand. Okay? The other option I have, depending upon the skill, right, is we can increase the area over which the force is applied. So instead of increasing the distance over which, the time over which the force is applied, we can impact the area that the force is applied. Right? So I don't know very much about judo, but if you watch a piece of judo video, when you get thrown, you'll see them slap their arms out, right, as they hit the mat. Because putting my arm out increases the distance over which the force of that throw is applied, and maybe it doesn't hurt quite so much. I don't know, it always looks like it hurts to me, right? So one of the things you'll see these days, I have to go back to gymnastics because that's my background. You guys have to try and think of examples within your own sphere of experience. But one of the things you'll see these days, which would have given you a penalty deduction when I was competing, is you'll quite often see the gymnasts land with their feet apart and pull their feet together as they stretch up. That's number 2, right? If I come down with my feet apart, I've increased the area that the force is being applied to, and it's easier to control the landing and then stand up. In my day, you had to land with your feet together, otherwise there was a deduction, right? But the sport has evolved and changed. Okay, let's change tack a little bit. All this Newton's laws and forces and things. Let's look at some concepts around the idea of being stable and being on balance. Okay? Because being stable, being on balance are important in many sport skills, right? It's not a lot of help if I catch the ball and then before I have the chance to throw it to someone, I fall over. Right? The distinction between the two terms, stability is my ability to resist falling, and balance is my ability to maintain equilibrium. Right? So many skills involve what we call a stability-mobility trade-off, right? In order to be more mobile, I have to allow myself to become less stable. So when we look at the development of walking and running, that's a huge part of what we see happen, right? The way the brain organizes that skill is maximizing this stability-mobility trade-off. So remember Thursday we talked about the center of gravity, right? And that to move the body, we want to either apply force linearly through the center of gravity, or if we want rotational movement, then we're going to apply the force outside of the center of gravity. Well, that's important when we come to this idea of stability. All right? The first thing we want to do to increase stability is widen our base of support. Right? The next thing we want to do is lower our center of gravity. So this is much more stable than this. Would you agree?
Yes.
Right? So if I'm a football coach, then I want them down here, right? Because plus big, right? So I give them masses of inertia because they're huge. Then I widen their base of support and I drop their center of gravity, and good luck to the person that's running in there trying to knock them over, right? Okay.
You also have more power as well.
Yes, yeah, right? Because you've already extended, that's an exercise physiology point, you've already put an extension on the quad that allows the quad to contract faster. If I want to increase my balance, right, then I have to do this first, increase stability. To increase stability, I have to improve my strength my coordination, and my proprioception, so my brain's understanding of the sensory information it's receiving. All right, last couple of slides, guys. We're nearly there. So in everyday language, we often use the word balance when what we mean is stability, okay? If I want to be on balance, my center of gravity has to be within my base of support. So if my feet are wide apart and you push me, you have to push me a long way before my center of gravity moves outside my base of support. If my feet are together, my base of support is small, you don't have to push me very hard at all to topple me over. Right? Doesn't necessarily have to be in the middle of the base of support, just within the base. So we want to visualize, like, whatever is touching the floor, what's the shape, and we'll do this as one of the exercises for the review to help you out a little bit. But what's the shape of my base here, right? So the picture that I have on the slide is someone going to do a squat, right? And it shows their base of support. If they want to maintain their balance while they're doing their squat, or if they're doing a snatch, right, then their center of gravity has to stay within that shape. Otherwise, if I lean too far forwards as I snatch, I'm going to fall out. Right? If I squat and I lean too far, I've got too much weight in my heels, my center of gravity moves outside my shape, and I fall over backwards, and you've got to hope that you have a good spotter there. Right? So stability is really a measure of how easy or hard it is to perturb someone's balance, right? Can I disturb their balance enough to get them off balance? So when we look at running as a skill, you'll see that running is basically falling, right? Because if I stay on balance, and I pick my foot up, right? I could do this all day, right? I'm not going anywhere. In order to run, not only do I have to push down and back, but I have to be willing to allow my center of gravity to fall outside my base of support. Right? So I fall and I step. So, handstand number 1. You can see her hands are wider than her shoulders. So she has increased her base of support. And by dropping her legs into this split with bent knees, she's dropped her center of gravity lower to the floor. So this handstand is highly, highly stable. Right? This handstand, she's on one hand, her body is straight and long, her legs are together, her center of gravity is high, compared to her base of support. This is very unstable. Right? The less stable the skill is, typically the more difficult the skill is. Right? When we start to look at our movement skills and our developmental trends, the brain will produce the movement pattern that will keep you the most stable when you're a beginner. Right? Because the brain's job is to keep you safe. Right? It doesn't want you falling over and smacking your head on the floor. So when we look at these movement patterns that we get, the brain starts out with something that's very stable, and gradually when we look at the stages of development, we'll see that the skill becomes less stable as the person gets more experienced, and the brain is reorganizing the movement pattern to create something that's more efficient or effective. Okay? And just to point out to you, check when you're going through this chapter, check page 40 and 41, because they're looking at how do I use these principles of motion and stability to coach and teach movement skills, right? How do I identify where the error is occurring? What do I say to correct the error? All right, so they've got a step-by-step process there that's very beneficial. All right, last slide is just a summary of what we've talked about. On Blackboard, there are 2 articles to help you with this information. One of them is by Dr. Gagan and Dr. Getchell. Dr. Getchell is one of the authors of our textbook, right? And it was printed in JOPED, which is the Journal for PE, Recreation and Dance. So it's a very user-friendly article to read. And it's looking at applying Newton's apple to elementary physical education. So it talks about how do I take these principles and use them to make me a better teacher, to provide good feedback to my students. All right. The other one is called the Biomechanical Concepts for the Physical Educator by Dr. Strohmeyer. All right. Again, it was in JOPED, so it's a very applied, user-friendly article to read. Please, if you're not going PE teacher route, don't think that doesn't mean that these don't apply to you. Remember that if you are a coach or an athletic trainer, you are still basically a teacher of movement skills. Okay? So read both of those. All right. Questions quickly? It's time to finish. It's a lot of information. Okay? One of the things I don't like about Tuesday, Thursday classes is that this class is so long and you're getting dumped with a lot of information. So we've basically done chapter 3 in a little over 1 class, and typically I would have taken 2 or 3 classes to do that information. Right? So I know it's a lot to try and absorb at one time, but that means that the onus is on you to make sure that you practice, right? Practice. Go back and look at the information again and again. And then if you have questions, let me know. Okay? Okay, I'm gonna sign off. Bye. See you tomorrow for lab.